Somewhere 49 light-years away, a rocky planet held an atmosphere. For the first time, astronomers found one in a habitable zone, but when they looked again a year later, the signal was almost gone. The planet is called LHS 1140b. It's a super-Earth, 5.5 times heavier than ours, a little wider. It orbits a red dwarf every 25 days, close enough that water could liquid on its surface. Close enough for life, or something like it. But here's what made the discovery matter. For decades, astronomers have hunted for atmospheres on rocky exoplanets. Most detections came from gas giants, bloated worlds where a thick atmosphere is easy to spot. Rocky planets in habitable zones were supposed to be different. Their atmospheres were supposed to be too thin, too hard to see. This one defied that. And the method used to find it promised to change how we search. The team used an instrument called WINERED, mounted on the Magellan Clay Telescope high in the Andes Mountains of Chile. They watched the planet pass in front of its star, a moment called transit. As the planet crossed the star's face, that starlight passed directly through the upper atmosphere. Certain atoms in that atmosphere absorbed and re-emitted the light in distinctive patterns. Physicists call this transit spectroscopy. The researchers hunted for helium, one of the lightest elements and the easiest to strip from a world. Helium glows in a distinctive infrared signature when it's heated and escaping into the vacuum. And in 2024, they saw it. Clear signal, definite detection. The atmosphere was real. Unmistakable. But then came the twist that nobody anticipated. When they pointed the telescope back at the same system in 2025, the helium signal was far weaker, almost undetectable. The same planet, the same instrument, the same method. Yet the escape had dropped to nearly nothing in less than a year. This wasn't the kind of thing that happens twice, and you shrug. This was a planet actively shedding and restoring its atmosphere on timescales that nobody had predicted. Somehow, the escape was variable. Somehow, it was on. To understand why, you have to know what LHS 1140b is up against. Its star is a red dwarf, smaller and cooler than our sun, but what it lacks in size it makes up for in ferocity. That proximity matters. The planet orbits every 25 days at a distance that would make it scald if it were Earth in the same orbit. Closer than Mercury to the sun. The star bombards it with X-rays and ultraviolet radiation, thousands of times more intense than Earth receives. That extreme heating energizes the upper atmosphere. Atoms vibrate so hard that they break free. Helium, being light, escapes first. It simply drifts away into space. Heavier elements follow behind. Over millions of years, a world can lose most of its protective blanket this way. Atmospheres stripped by stellar radiation are not rare, but catching one mid-escape, measuring the rate with precision, and then watching that rate change between observations, that was new. The significance of this detection goes far beyond a single planet in a single system. For the first time, astronomers had confirmed an atmosphere on a rocky exoplanet inside a habitable zone using actual observations, not just educated guesses or theory. No biosignatures, no evidence of life, no proof of habitability, but an actual measurable atmosphere on a world where liquid water could exist on the surface. That opens a door that's been sealed for decades. If we can detect and characterize atmospheres on rocky planets in habitable zones, then we can study them. We can measure what they're made of, how they change from year to year, how they respond to stellar radiation and stellar cycles. We can start to ask which of these worlds might hold stable atmospheres, and which are being stripped bare by the very stars they orbit. The variability in helium escape hints at something deeper about how planetary atmospheres behave under extreme conditions. Stellar activity might not be constant. Red dwarfs can flare and cycle, sending surges of radiation toward their planets on unpredictable timescales. The amount of high-energy X-rays and ultraviolet hitting the planet could pulse and wane. or the planet's own state might matter. Its magnetic field strength, the density of its upper atmosphere, the way it rotates and weathers its star's fury. The team found one snapshot of an atmosphere in flux, one moment in time. But they don't yet know what drives the dramatic switches between low escape rates and high. Is it magnetic weather? Is it the star's activity? Is it something intrinsic to the planet itself? Those answers will require more observations, more planets studied the same way, more years of patient watching. LHS 1140b sits 49 light-years away. That distance means we'll never visit it, never take a photograph close-up, never know if anything lives there. But we can now measure its atmosphere. We can watch it change. We can use methods like transit spectroscopy to study dozens of these worlds in coming years. The discovery was published in Science in July 2026. It's one data point. But it's a crossing of a threshold. Rocky planets in the habitable zones of distant stars are no longer invisible. Their atmospheres can be found, their properties can be measured. And the questions that follow, which atmospheres persist, which are stripped away, which might harbor life, suddenly shift from theory into observational astronomy. The broader context is that we are entering an era where exoplanet atmospheres are becoming data, not speculation. The James Webb Space Telescope has already detected the signatures of water and other molecules in the atmospheres of distant worlds. Those observations have mostly come from gas giants, but the capability is expanding downward to smaller, rockier worlds. LHS 1140b's atmosphere, detected not by JWST, but by ground-based infrared spectroscopy, shows that method matters less than signal. If a world is the right size, the right distance, and you ask the right questions, you can find answers. You can map an atmosphere. You can measure its escape. You can begin to understand what it means for a world to be, or not to be, habitable. The variability of the helium escape also raises a deeper question about habitability itself. An atmosphere that's being stripped by radiation is an atmosphere under threat. But the fact that it can vary, that it can sometimes be strong, sometimes weak, suggests that the planet isn't in a simple state of slow death. There's flux. There's change. Whether that's good or bad for life, if life were there, is unclear. A world losing its atmosphere might also be one that's in the process of geological change, of renewal, of evolution. Or it might simply be a harsh place where nothing survives. We can't know without looking deeper. But now we can look. Now we can see.